examples of backward propagation. And we're going to start with, well, we're going to see two examples. The first one is a very simple feed forward. Every layer is applied by applying a function f over the previous layer with one parameter per layer. So hi will have the parameter theta I, a single number, a single parameter. And y is simply the last layer. Very simple network. And we assume that there is no regularization. Loss is simply the risk on the training set T, and we write it simply as a risk of a Y. And then we need to compute the gradient of the parameters with respect to the loss. The forward step is really simple. With respect to the current values of the parameters, we compute the network, starting with H0, then H1, all the way to HL. And we are done. Now we are going on the backward step. And for every I, we have the gradient I, which is the gradient of theta I on the loss, okay, which we also mark it this way, and this is a scalar. And every layer L, or every layer I, starting from L and going all the way to layer 1, is going to compute GI and provide the layer I minus 1 with the information that it needs to compute GJ. Okay, GJ for J smaller than I. That's all. That's what we said earlier. Okay, let's start with the last one, gradient GL. So GL is the derivative of theta L with the loss, and which is basically the risk over the previous layer. Okay. Uh, but if you look at this term, HL minus 1 is actually a fixed number now, right? It doesn't involve theta L. And this whole function is something, just a function of theta L. We can simply compute the derivative directly on that. We don't need anything from the lower layers. It doesn't involve any theta I for I smaller than a L. What happens to such AI? So let V be HL minus 1, this part. Okay? If you're looking at the J that is smaller than L, then with the chain rule, we will get GJ with theta of the derivative of uh, theta J on the loss, which is the derivative of V on the loss and the risk, times the derivative of theta J on V. Just a simple application of the chain rule. But now, okay, and do realize that this part is, the dimensions match. Okay, this is a row vector because it has several inputs, and the derivative of theta j on v is a column vector because v has multiple outputs. Okay, so this part, again, it doesn't involve any inner parameters. V is now fixed, and we can compute it directly without looking at the lower layers. Okay, so we provide layer L minus 1 with this number P, and we ask it to compute not only its derivative on the layer L minus 1, the output of L minus 1, but rather multiply it by P. Okay, that's what we send to this layer. Okay, so now we're at layer I, which is smaller than L. We got some row vector P from the higher level, and we need to compute um, for all j smaller or equal than gj, which is P times the derivative of theta j on this layer, hi. Okay. Uh, so for j, when j is I itself, okay, what we have here again doesn't involve um, any other parameter. It's all fixed, v is fixed, and the only variable is theta I, and we can simply compute the derivative. Okay. Now, when j is smaller than I, then again we apply the chain rule. The derivative of theta j on the function is the derivative of the value v on fi times, and then v, is the lower level, the derivative of theta j on v. Okay, and this part is something that we can compute. Now it is actually a matrix because it has several inputs and several outputs, and this is a vector. This part we know how to compute at the ith layer, and this layer we send um, this is the task. This part is the task of the lower layers. Okay, so we compute this part directly, and then what we send to the lower layer is not just p, but p times what we computed here, so that it will actually compute what it takes. P times this part times, and then it will compute the derivative on theta j. Okay, so that's the idea. Let's look at another example, the MLP. Okay, every layer is a linear combination of the previous layer, followed by an activation, phi, and the last layer is softmax on the HL, okay, on the last linear layer. Okay, so now we denote the linear combination by smaller of I, small AI, and then HI is really activation on AI. Okay? But now we're going to have a regularization term, omega theta, in our loss function. So each layer I, we need to compute the GIA, basically the derivative of the AI parameters and the derivative of the BI parameters. Okay? Because this is how it is defined. Now, our loss function is, right, the risk over a y, risk over softmax of HL. We can now apply the chain rule and say each GI x is either a or b, is the derivative of HL of this risk function, okay, on applied to HL, times the derivative of xi over HL plus the derivative of xi on the regularization. Regarding the regularization, it doesn't involve actually the outputs of other layers. This is something that we can compute directly in each layer or once outside it, because well, basically we have for every parameter we fix the other parameters and just compute the risk function, the regularization term. So the regularization will ignore it, okay? And what we need to do now is send the uppermost layer, computes this part, this gradient on HL, which is something that we can compute without looking at the previous layers. This is our P, and we're going to send it to the lower layers. And now P is a matrix. Okay, so it remains for the layer I to compute the derivative of our parameters on HL. And that's what we're going to do. So we have AI is this part. The chain rule gives us that the derivative of xj on hi is the derivative of AI, okay, on this function with the activation on AI times the derivative of xj on AI. Okay, and as usual, this part doesn't involve any parameters because now that we consider them as fixed. Okay, so we can compute this part directly in our layer, and it remains to do this part. Okay, now if you if j is I, well, xi is yeah, the layer is I, we can compute this part directly on the ith version, because on the ith layer, because it involves the gradient involves only the parameters of the ith layer, okay, xi. For example, if xi is the parameters bi, okay, then their derivative is actually the identity matrix I, because they just appear here without, just directly. Okay, so that's for I. But if j is smaller than I, okay, and we need to compute the derivative of a j, okay, or xj on this part, basically, uh, then we again apply the chain. Okay, so this is theta of hi minus 1. This is our hi on I. Uh, times the derivative of xj on hi minus 1. I just applied the chain rule again. Now, do realize that the derivative of hi minus 1 in this AI is simply this matrix, A, big A of I. Okay? So what do we get in the end of the day? We had this part of the product that we multiplied by this one, which turns out to be this part, which is simply AI, times this part that we need to compute. So instead of sending P to the next layer, we send it P times this component here times this component here, which is AI. Okay, and continue on. Okay, so that was it. That's the idea. Similar idea, but you know, slightly more details. Now let's look at some other aspects. When we look at what we did in the in the backward propagation, we see that we every time we added another thing to the product, so we multiply and multiply and multiply. And what happens when we apply these repeated multiplications is that we might lose control over the weights. They can shrink in an uncontrolled manner or grow. So when they shrink, that's the issue of vanishing gradients. They become too small and their impact is small and everything converges too slowly, learns too slowly. If they're big and they can become bigger and bigger, everything might diverge. So you're not really um, converging, okay, to anything that you learn. Okay, so that's called gradient explosion. Okay, when you do not control the gradients from that perspective. Okay, and this is a severe issue when your network is deep, it has many layers, or it is recurrent, then you apply it again and again. And there are several ways of mitigating that. We're not going to learn them, but I just want you to be aware of the problem and the existence of solutions there for that. One very popular idea is weight initialization from some nice distribution like Gaussian, the Javier initialization, for example. Okay, and this is something that helps avoiding this issue. Or you normalize every layer, making sure that it doesn't explode or doesn't become too small. It is normalized. Or we apply skip connections. Skip connections allow every layer in the training to accommodate the previous layer, the input of the previous layer directly without going through the transformation. Okay, so that gives the opportunity of ignoring whatever explosion or vanishing happened in the previous layer. Okay. And gradient clipping is simply, you just stop or you just refuse the update of the gradients when they become too big or too small. Okay, so these are different ways of dealing with vanishing and exploding gradients. And the last thing I want to teach very quickly in this part is the concept of a dropout. And dropout is used for basically for a regularization, for avoiding overfitting, where you basically introduce, say, problems from the training algorithms or the training algorithm so that it will need to deal with this problem or noise that you're producing or lack of information, and then be smart on that respect and not rely too much on nuances. Okay, so this is the main idea. We mitigate the overfitting by randomly concealing stuff, deactivating neurons, and encouraging the learning to tolerate errors. Okay, now when you apply it, it looks, in machine learning libraries, just as an ordinary unit activation. Okay. What is special about it is that it is activated in the uh, gradient descent part or in the gradient computation randomly. Okay, not deterministically. But this happens only in the training. It is actually ignored in the evaluation. Okay, in the test and validation phases. Okay. And okay, so how do we control that? Well, there's a hyperparameter p, which is the probability of dropout. So instead of x or x, we're using x times m divided by 1 minus p. M is either 0 or 1. So it is when it is 0, x is 0. Basically, it is mass disappears. When it is 1, we divide it by 1 minus v so that we retain the original expectation of p. Okay, so the expectation is the original value. And that's the idea. Okay, here is an illustration. So you have this network, and these small circles are your dropouts. Okay, so you can see that when you apply the dropout during training, some of their outputs disappear. Okay, for example, this one, we remove this edge from it, and this one, instead of having three edges, it has only two ones. And that's it.